This is the third part of the module transmission characteristics of an optical fiber. In the first and second modules we had seen that the attenuation and intermodal dispersion, they limit the repeaterless length of the link. In this lecture we would look into what would be the implication of the wavelength content of the source. The flow of the lecture is something like this. We will talk about chromatic dispersion, then what is an optical pulse, what are phase and group velocities, then material dispersion. Then since the fiber is telecom fiber is made of pure silica glass, so we would look into the material dispersion of pure silica glass, and then what is the total dispersion in a multimode fiber. So I come back to this slide again, where we had seen that the repeaterless length of the link for a given data rate depends upon attenuation and broadening of the pulse. Broadening of the pulse we had already seen in the last lecture, the material dispersion where light is coupled into various ray paths and these ray paths take different times to reach at the output end of the fiber. So light coupled into these various ray paths takes different times to reach at the output end of the fiber, and this causes what is known as intermodal dispersion. Today we would see if we have a source and which has certain wavelength content, what would be the implication of this on the broadening of pulses. I know that if I launch a beam of white light into a prism, then I see dispersion, I see various colors appearing at various angles, and this is purely due to the refractive index wavelength dependence of refractive index of the material of the prism, and the geometry of the prism enables these different colors coming out at different angles. This is known as chromatic dispersion. Now if I have a fiber then made of glass, then fiber material also has this characteristic. The refractive index of the material at different wavelengths is different. What would be the implication of that? So for that, let me first look at how do I transmit data in an optical fiber. I transmit data in the form of pulses, and when I switch on a laser and switch it off, I generate a pulse. If I look into this pulse, then as I will see a little later that this pulse is essentially a superposition of large number of harmonic waves of different wavelengths or slightly different frequencies, and when I use a light source like LED or a laser diode for creating these pulses to send data into an optical fiber, then these light sources have finite line width. For example, an LED has a typical line width of 20 to 30 nanometers, while a laser diode, although it is highly monochromatic, it also has a certain line width. Its line width can be of the order of a nanometer, and if it is very highly chromatic and very good laser source, then it can be 0.1 nanometers or so, but it has certain line width. So all the wavelength components which fall in the line width of these light sources would now experience different refractive index of the material, and they will travel with different velocities, and that should give rise to dispersion. To understand that, and this kind of dispersion is known as material dispersion. To understand that, let us first find out with what velocity this pulse travels in an optical fiber or in a material. Even if we forget about optical fiber, even if it is infinitely extended material, with what velocity this pulse travels in the fiber. Does it travel in the same way as a continuous wave, a harmonic wave? Let us look into it. So, if I first consider a single harmonic wave of angular frequency omega, which is propagating in z direction, then I can write the displacement of this wave as y is equal to a cosine omega t minus kz, where a is the amplitude, omega is angular frequency, k is the wave vector. And if I plot it at certain z, if I observe the amplitude of this, the displacement of this at certain z for all the times, then it will vary with time something like this. Now, the velocity of phase fronts I can find out from here, since what is the velocity of phase front? What are phase fronts? Phase fronts are the surfaces of constant phase, and here the phase is omega t minus kz. So, surface of constant phase would be given by omega t minus kz is equal to constant. Now, I can find out the velocity of phase fronts from here. I just differentiate it, then omega dt minus k dz is equal to 0. That is what I have there, and this will give me dz over dt is equal to omega over k, and this dz over dt is nothing but the velocity of the phase front, and this is known as the phase velocity. So, when a single harmonic wave travels in a medium, then it goes with this velocity. For light waves in free space, this is nothing but c and can be given by omega divided by k naught, where k naught is the wave vector in free space. Now, let us consider two harmonic waves of very close angular frequencies omega 1 and omega 2 and very close wave vectors k1 and k2. So, I can write them as y1 is equal to a cosine omega 1 t minus k1 z and y2 is equal to a cosine omega 2 t minus k2 z. For simplicity, I have taken the same amplitudes of these waves. Now, I superpose them. When I superpose them, then y becomes y1 plus y2 given by this, and if I simplify this, what do I get? I get y is equal to 2a cosine omega 2 minus omega 1 by 2t minus k2 minus k1 by 2 z times cosine of omega 1 plus omega 2 by 2t minus k1 plus k2 by 2 z. Now, since omega 1 is very close to omega 2 and k1 is very close to k2, let me write them down as omega and k, and also assume that omega 2 minus omega 1 is equal to delta omega and k2 minus k1 is equal to delta k. Then I can write this down as 2a cosine delta omega t by 2 minus delta kz by 2 times cosine omega t minus kz. Now, let us examine this. If I examine this, this is nothing but a term which contains a frequency omega, while this term contains a very small frequency delta omega. So, this is nothing but high frequency constituent waves, and this is the envelope which is low frequency. If I plot them, if I plot this y now as a function of t for any given z, what do I see? The amplitude goes something like this. So, I have this red one is the envelope, low frequency envelope, and the blue one is the high frequency constituent waves. And if I plot the intensity of this, which is proportional to y square, then it comes out like this. So, what I have observed that if I superpose two waves, I make groups, a train of groups, I generate a group of waves, and this group of waves are traveling with certain velocity, which is the velocity of the envelope from here, and if I find out the velocity of the envelope from here, it comes out to be delta omega over delta k. So, this is group velocity. So, this group of waves travel with velocity Vg, which is delta omega over delta k. However, the constituent waves, individual constituent waves, they travel with velocity omega over k, which is the phase velocity of the constituent waves. So, this is a series of group, but if I have a pulse, an isolated pulse, then it is a group of very large number of such harmonic waves with continuous frequency variation in omega and k. So, instead of taking the superposition of two waves, I take the superposition of 100 waves and then 1000 waves, then I can find out that these groups are separated, okay, and I can create an individual group or wave packet. This is also known as wave packet. If I have this very large number of harmonic waves with continuous variation in omega and k, and in such a situation delta omega over delta k would now become d omega over dk, and the group velocity will be given by d omega over dk. So, now if I send this pulse through a material, that material can be the material of optical fiber, then it is a group of waves. And now I want to find out how the different frequency components travel in this material and what is the implication of that. I know the constituent waves of this wave packet or the pulse will have propagation constant given by k naught times n omega, where k naught is omega by c and n of omega is frequency dependent refractive index of the medium. Now, I can find out the velocity from here, group velocity, because this pulse will travel with the group velocity Vg. I know Vg is equal to d omega over dk from the previous slide. I have Vg is equal to d omega over dk, but remember that ultimately what I want to do is I want to find out the transit time through L length of the fiber, and that would be given by L by Vg. So, instead of working out the expression for Vg, let me work out the expression for 1 over Vg, because that is how it will appear ultimately. So, I find out 1 over Vg from here. 1 over Vg would be dk over d omega. So, I take differential of k with respect to omega, I take derivative of k. So, it comes out to be 1 by c n of omega plus omega times dn over d omega. And since I work with wavelengths instead of frequencies, in practical situations I always work with wavelengths. So, let me obtain this Vg in terms of wavelength lambda naught. Lambda naught is given by 2 pi c over omega, and I have Vg in terms of omega like this. So, now let me find out this omega times dn over d omega in terms of lambda. So, omega over dn over d omega would be 2 pi c over lambda naught times dn over d lambda naught times d lambda naught over d omega, and lambda naught is given by this. So, it would be simply 2 pi c over lambda naught dn over d lambda naught times minus 2 pi c over omega square, and omega again I can put as 2 pi c over lambda naught, and if I do that I get omega times dn over d omega is equal to minus lambda naught dn over d lambda naught. So, I put it back into this expression and I get the expression of 1 over Vg in terms of wavelength. So, 1 over Vg is now 1 over c n lambda naught minus lambda naught times dn over d lambda naught. Now, look at it. If I have a single wave having wavelength lambda naught and there are no other wavelength components, then this dn over d lambda naught is 0, and I simply get 1 over Vg is equal to n by c, or Vg is equal to c by n, which is nothing but the phase velocity. But when I have a group of waves, then this extra term comes into picture. From here you might think that in this way the refractive index which is felt by the group of waves has decreased. You can see that now the refractive index from individual wave to group of waves now changes as n lambda minus lambda naught times dn over d lambda naught. So, the group of waves will feel this refractive index of the medium. Has it decreased? If I compare it with the individual wave, no, because dn over d lambda naught is negative. So, the refractive index, which is also refractive index of the group of waves, which is also known as group index, has basically increased. So, group of index has increased, and this is how the group velocity has decreased now. So, individual waves they travel with faster velocity, but the group moves with a slower velocity. Group moves bit slower, much slower. Okay, others pull them down. One individual wave tries to move fast, but others says no, you cannot go that fast, and they pull them down. So, group index is always larger than the index of the individual wave. Now, let us find out what is the time taken in traversing length L of the fiber. So, this would be given by L by Vg and simply L by C times group index, and this group index is of course a function of lambda. Now, let us look at the spectral characteristics of the source, what wavelengths, what values of lambda naught I have. So, if I take the LED, then this is the line width, and if I take a laser diode, this is the line width, and all the wavelength components which fall into these line widths would now contribute here. They have different transit times. What would be the implication of this on the broadening? How much would be the broadening? So, it is very simple that if the source has a spectral width delta lambda naught, then the temporal broadening of the pulse would be simply given by delta tau is equal to d tau over d lambda naught times delta lambda naught, while considering only first order term. And since tau is equal to L by C, n lambda naught minus lambda naught times dn over d lambda naught, then this would be simply, now I just take d tau over d lambda naught from here. So, dn over d lambda naught minus dn over d lambda naught minus lambda naught times d2n over d lambda naught square times delta lambda naught, and this would simply be minus L by C times lambda naught d2n over d lambda naught square times delta lambda naught. And usually what we do, we define this broadening in terms of dispersion coefficient, and here it would be called material dispersion coefficient. Since the fiber length is measured in kilometers and the line width of the source is measured in nanometers, so I find the broadening of the pulse per kilometer length of the fiber and per nanometer spectral width of the source, and so the dispersion coefficient is given as delta tau divided by per kilometer length of the fiber per nanometer spectral width of the source, and we usually represent this delta tau in picoseconds per kilometer nanometers. So, this would now be simply minus lambda naught by C d2n over d lambda naught square. Let us work out with the dimensions here. So, if you go back, it is lambda naught, it is d2n over d lambda naught square. So, what I do now, I multiply numerator and denominator by lambda naught. So, I can write this down like this. The motivation for writing this down is that now I can get this as a dimensionless quantity. Okay. So now the dimensions are coming from here. So, let me express lambda naught in micrometer and C in kilometers per second, then the dimensions would be seconds per kilometer times micrometer, and let me convert it into picoseconds per kilometer nanometers. So, this would be 10 to the power 12 picoseconds per kilometers times 1000 nanometers. So, it would simply be this much times 10 to the power 9 picoseconds per kilometer nanometer. So, you can use this expression to calculate material dispersion coefficient in picoseconds per kilometer nanometer, provided that you put the velocity of light c in kilometers per second and wavelength of light in micrometer. So, that is what I have written here. So, now let us look. So, if I again go back and see that this material dispersion coefficient depends upon how the refractive index of the material changes with wavelength. So, I need to know what is the second derivative of n with respect to lambda, and this is the characteristic of a material. For different materials it would be different. So, different materials will exhibit different material dispersion characteristics. Let me do this for pure silica glass. It is fused silica, and the variation of refractive index with wavelength of fused silica glass is given by this, where various constants have these values and lambda naught is measured in micrometer. What is done is basically you measure the refractive index of the material at different wavelengths and then fit this kind of relationship to find out the values of these constants. So these values are also experiment dependent, but these are quite accepted values in the literature. So, now what I do, I find out the variation of n with respect to lambda. I plot the variation of n with respect to lambda of fused silica glass, and it looks like this. Then dn over d lambda naught in the units of micrometer inverse, it goes like this, and what I find that it changes its slope from here to here, and it has got a maximum somewhere here, and it tells me that, and remember that in dispersion coefficient I need to have d2n over d lambda naught square, which means that it should cross 0 somewhere here. So now I plot d2n over d lambda naught square in micrometer to the power minus 2, and I see the variation looks like this, and it crosses 0 somewhere here. Okay. And if I find out d2n over d lambda naught square at certain wavelength, say 800 nanometer or 0.8 micrometer, which was the wavelength used earlier for optical fiber communication, around 800 or 850 nanometer. So I find that this d2n over d lambda naught square is about 0.04 micrometer to the power minus 2. And here if I plot this material dispersion coefficient using this in picoseconds per kilometer nanometer, then corresponding dmat goes something like this. And I find that since there is 0 crossing around this wavelength, so material dispersion is 0 at this wavelength, and this wavelength is around 1.27 micrometer. Now let me work out some numbers for a typical LED source. If I take lambda naught 0.8 micrometer, delta lambda naught 25 nanometer, and from here if I find out dmat, I have already seen that d2n over d lambda naught square is 0.04 micrometer to the power minus 2. So if I put these numbers here, I find that material dispersion coefficient at this wavelength comes out to be about 106 picoseconds per kilometer nanometer. Corresponding broadening will come out to be minus 2.7 nanoseconds per kilometer. Well, broadening would be always, I have to take the magnitude of that. Okay. This dispersion coefficient is negative. What is the meaning of negative and positive? We will learn as we go along, but there would be a broadening of about 3 nanoseconds every kilometer. If I take a laser diode at 1.55 micrometer and delta lambda naught about 2 nanometers, at this wavelength d2n over d lambda naught square comes out to be minus 0.004 micrometer to the power minus 2, and it gives me material dispersion coefficient as 20 picoseconds per kilometer nanometer, and now the broadening is only 40 picoseconds, only 40 picoseconds. So you can see when I go from an LED at 800 nanometer wavelength to a laser diode at 1550 nanometer wavelength, the material dispersion comes down drastically from 3 nanoseconds per kilometer. If you go back 3 nanoseconds per kilometer to 40 picoseconds per kilometer, and if I use a wavelength around 1.27 micrometer, then it is almost 0. So this wavelength is also known as zero material dispersion wavelength, and that is why the earlier fibers, the fiber which is already laid on seabed, okay, most of that fiber is optimized around 1.27 or 1.3 micrometer wavelength. Now let us look at pulse propagation at different wavelengths. This is the LED at 800 nanometer with line width 25 nanometer and broadening of 2.7 nanoseconds per kilometer. So if I now send this pulse, I see that it broadens very quickly. When I use a laser diode at 1550 nanometer wavelength, which gives me a broadening of 40 picoseconds per kilometer nanometer, then it also broadens the pulse there, but the broadening is not that much. But if I use 1270 nanometer laser diode, then the broadening is very small, around 1 picoseconds per kilometer length of the fiber, and at this wavelength the pulses retain their shape over very long distances. Then there is total dispersion in multimode fiber. Total dispersion will comprise both the intermodal and material. So, I can then find out the total dispersion by using the information of intermodal as well as material dispersion. Then the maximum bit rate I can find out if I know the total dispersion by 0.7 over delta tau, and I know that Bmax times delta tau should be less than 1, but I have taken this factor 0.7 here. It is corresponding to non return to 0 coding. Now, I take two examples for a step index multimode fiber where N2 is equal to 1.45, delta is equal to 0.01, and I have wavelength which is 850 nanometer, LED of 25 nanometer line width. So, here delta tau m material dispersion is about 2 nanoseconds per kilometer, while intermodal dispersion is 50 nanoseconds per kilometer. So, total dispersion comes out to be 50 nanoseconds per kilometer, this dominates, and if I find out Bmax from here, it is about 40 Mbps over a kilometer. If I take a graded index fiber, graded index multimode fiber with Q is equal to 2, which has got parabolic index variation, then I find that intermodal dispersion comes down to 0.25 nanoseconds per kilometer, while material dispersion is 1.7 nanoseconds per kilometer. So, this dominates. Okay. Total dispersion is about 1.72 and Bmax can be 400 Mbps over a kilometer, 400 Mbps over a kilometer. So, it increases from 14 Mbps to 400 Mbps. So, what we have learnt in this lecture, that an optical pulse comprises a group of large number of harmonic waves of different frequencies or wavelengths. These constituent waves of pulse have different phase velocities. The envelope of the pulse moves with a velocity called group velocity. Different velocities of constituent waves give rise to what is known as material dispersion, and material dispersion coefficient we usually represent in terms of picoseconds per kilometer nanometer. Pure silica glass has 0 dispersion around 1.27 micrometer wavelength, and total dispersion will contain now both intermodal as well as material dispersion. In a multimode step index fiber, the intermodal dispersion will dominate, while in a graded index multimode fiber material dispersion dominates. So, this is all about some basic transmission characteristics of an optical fiber. In the next few modules, we will do some rigorous analysis of light propagation in optical fibers. Before that, we will understand how light propagates in infinitely extended medium, then a very simple planar waveguide. Okay. So, we will do in the next few lectures now. Thank you.